This video is about Section 4.5, where we'll discuss irreducibility of polynomials with rational coefficients. The first thing to know about this section is that even though we're going to be focusing primarily on polynomials with rational coefficients, many of the results in this section are actually cast in terms of polynomials with integer coefficients. We can always take a polynomial with rational coefficients and turn it into one with integer coefficients just by multiplying by some appropriate constant. Like for instance, if we had f of x equals, 1/3 x cubed plus 2x squared plus 2/5 x plus 1, we can multiply that by 15 and produce a new polynomial whose coefficients are all integers. The important thing to notice is that this original polynomial f of x, that's going to be irreducible over the rationals if and only if this constant multiple of f of x is irreducible. So any sort of problem involving irreducibility over the rational numbers can be translated to a problem where the original polynomial in question has integer coefficients. And that's good for us because we're going to be able to then use our knowledge of the integers, our special knowledge of the integers, to help determine if a polynomial is irreducible over the rational numbers. So our first theorem of the section is a classic theorem called the rational roots theorem that you probably have seen before at some point. This is a theorem about polynomials with integer coefficients. And here we suppose we have a non-zero rational root r over s of this polynomial, where the r and the s are relatively prime. Then the theorem tells us that the numerator r must be a divisor of the constant term a naught, and the denominator s must be a divisor of the leading coefficient, a sub n. So the proof of this theorem isn't extremely long, so we can go through it. So remember, r over s is a root of f. So when we plug r over s into f, we get 0. Now, that's not going to be changed if we multiply by s to the n. And multiplying s to the n has the effect of clearing out all of the fractions in the expression f of r over s. And what we wind up with is this big long sum right here. Now what we can do is take this very first term of that sum and move it over to the left side of the equation, and then we obtain this new equation here, where we have minus a sub n r to the n equaling this bunch of stuff on the right. Now the thing that's important about that stuff that's left on the right is that you can factor out an s from all of that stuff. And so what that tells us is that s is a divisor of a sub n times r to the n. But remember that s and r are relatively prime. And so we had a theorem back in Chapter 1. I think it was Theorem 1.5 that told us that if you have something dividing a product and that something is relatively prime to one of the things in the product, then it must divide the other thing. So from that Theorem 1.5, I believe that's the theorem anyway, we're able to conclude that s divides a to the n. Now there's a similar statement about r dividing a naught, and that proof is very similar. So you go back to our original equation right here, And instead of bringing the a sub n r to the n to the other side, you just bring the a sub naught s to the n to the other side, and then factor an r out of the things that remain on the right side. Okay, so that's the proof of the rational roots theorem. And then we have an example like this. So let's suppose we start with this polynomial with integer coefficients, and we want to know what its possible rational roots are. Well, we look at the divisors of 3, which are plus and minus 1 and plus and minus 3. And then we look at the divisors of this leading coefficient 2, which are plus and minus 1 and plus and minus 2. And what we do, or what the rational roots theorem tells us to do to find the possible rational roots, is to take all possible quotients of divisors of 3 over divisors of 2. And if we do that, we wind up with this list of 8 numbers. Now, we might complain that that's a lot of numbers to check to see whether they're rational roots. However, it's better than checking infinitely many rational numbers. So if you try all of these numbers, plug them into f, you'll see that only minus 3 and minus 1/2 are roots of that polynomial. And in fact, by the factor theorem, that tells you then that x plus 3 and x plus 1/2 must be factors of this polynomial. And in fact, we can go through, and by long division, if we want to, we can write this as x plus 3 times x plus 1/2 times 2x plus 2. Excuse me, 2x. Yeah, 2x plus 2. Well, actually 2x squared plus 2. Right, it's a quartic polynomial. Okay, now one thing you might do, or one thing you might notice, is that we have a 2 here that we could factor out of this quadratic polynomial, and we could put it on this linear polynomial in order to make all of the coefficients integers. So why don't we do that? So this gives us x plus 3 times 2x plus 1 times x squared plus 1. So our next result asserts that the thing that we did at the end of the previous example is not a fluke. That is, if we start with a polynomial with integer coefficients and we factor it into a product of polynomials with rational coefficients, we can always fudge around with constant multiples in such a way that we can produce a factorization that has integer coefficients. Okay, that turns out to be a highly useful tool in determining irreducibility of certain polynomials. So I'll want you to read the proof of this theorem. And now let's talk about an example. Here we have a quartic polynomial with integer coefficients, and we want to show that it's irreducible over the rational numbers. So the first thing that we'll want to do is to check for rational roots. And the reason for that, remember, is that if there are rational roots, then by the factor theorem there must be linear factors. Okay? So the rational roots theorem tells us that plus and minus 1 are the only possible rational roots here. And if you test them, right? You plug in 1, you plug in -1. You see that neither one of these don't work. Neither one of them work, okay? So both of these fail. And what that says is that there are no linear factors. Okay, so no linear factors. Now, what that means is that the only way that we could possibly factor this thing is as a product of two quadratics. So let's set that up, right? We have this x to the 4th plus 3x cubed plus 1. And let's suppose that this can be factored over the rational numbers into some product, say mx squared plus ax plus b times nx squared plus cx plus d. Now, Theorem 4.23 says that if such a factorization exists over the rational numbers, then it must also exist over the integers, meaning that all of the coefficients that appear in this proposed factorization, we may assume that all of them are integers. Now, what you might notice, first off, is that if we take mx squared times nx squared, we'll get mn times x to the 4th. So that means that m times n must be equal to 1, right, in order to have the coefficients match up. So that means either m and n are both equal to 1, or m and n are both equal to -1. If m and n are both equal to -1, then just take both of these factors here, this one and that one, and multiply them both by -1, and that would force m and n both to be equal to 1. So we may as well assume that m and n are both equal to 1. And that leaves us with x squared plus ax plus b times x squared plus cx plus d. Now what we can do is equate coefficients, right? We multiply the thing on the right out, and we're going to see what sort of conditions exist amongst a, b, c, and d. So if I look at all the cubic terms, what I would get is I have an ax cubed and a cx cubed. So that means that there are a plus cx cubed altogether. So that's how many x cubed there are. But I know on the left there are 3 x cubed. And now I'm going to skip counting the squares for the moment, and we're going to go and we're going to count the x's. Well, how many x's are there? Well, there's an a times d x, and then there's a b times c x. And notice that on the left there are no x terms at all, so that's going to be 0. And then finally, we're going to count the constant term, right? So b times d is equal to the constant term of the polynomial, but I see on the left that the constant term is 1. So we get this collection of equations, and in fact, there are even more. There's another equation we could have written down for the x squared term, which we didn't write down because it turns out we're not going to need it here, but you could have written that down. So what can we do with these equations? Well, notice that b times d equals 1. If b and d were rational numbers, there would be a lot of solutions for that equation. But because we're allowed to presume that b and d are integers, that means that the only possibilities are b equals d equals 1 and b equals d equals minus 1. Now, if we suppose b equals d equals 1, and we look at the previous two equations over here on the left, we see that it gives us 3 equaling a plus c, right, from the top equation. But if b and d are 1, this second equation here tells us that a plus c equals 0, which is a contradiction. That cannot happen, right? Similarly, over here, we again get 3 equals a plus c. But now if b and d are minus 1, we get minus a plus minus c equals 0, which is the same as a plus c equals 0. And we get another contradiction. And so what we learn is that there's no way, there's no way to factor this polynomial into a product of quadratics that have integer coefficients. And by theorem 4.23, that's enough, together with the fact that there are no linear factors, to tell us that this original polynomial here that we started with is irreducible. The next result that we have is a funny little result called Eisenstein's criterion. Again, we start with a polynomial that has that's non-constant and it has integer coefficients. So what the theorem says is that if there's a prime number p that divides each of the coefficients except for the leading coefficient, and further, the square of this prime does not divide the constant term, then the polynomial is irreducible over the rational numbers. So again, this is a theorem whose proof is, I think, a bit longer than I care to write down on slides. What I would ask you to do is read this theorem. The key result from the past that plays a role in the proof of this theorem is theorem 1.5, which says that, if you have a prime and it divides a product, b times c, then that means that p divides one or the other. Okay, so let's try to use Eisenstein's criterion to do something interesting here. So in our example, we have this polynomial, 30 times x to the n minus 91. We're going to show that it's irreducible for every n bigger than or equal to 1. And what you can see here is that this polynomial, no matter what n is, satisfies Eisenstein's criterion for p equals 7, right? That's because we have that 7 divides 91. 7 does not divide 30. And 7 squared does not divide 91. So those facts together tell us that Eisenstein's criterion is satisfied for the prime p equals 7. And so that means that this doohickey here, this polynomial, is irreducible over the rational numbers. Now, this is actually something of an interesting result, because what it tells us is that there are irreducible polynomials over the rational numbers in every positive degree. That is, for every n bigger than 1, there's at least one polynomial of degree n that is irreducible over the rationals. And that's sort of tantamount to the theorem over the integers that says that there are infinitely many primes. Okay, it's maybe reasonable to think that in very high degrees there might not be any irreducibles because there are a whole lot of potential lower degree factors. If you have if you start with a very, very high degree of a polynomial. So this, if you're still paying attention, is what's called Frankenstein's criterion, and you can make of this what you will. Our last result of this section shows us how we can use finite fields to help us determine whether polynomials are irreducible over the rational numbers. So we start with a non-constant polynomial f of x that has integer coefficients, and we let p be just some positive prime number. And it's important for us to make sure that whatever that prime is, that it does not divide evenly into the leading coefficient. So the result says that if f bar of x is irreducible in zp, or over zp, then the original polynomial f is irreducible over the rational numbers. So the very first question that you must have is, what in the world is this f bar? Okay, so that's the new polynomial with coefficients over zp that you get by taking each of these original coefficients from the original polynomial and reducing them modulo p. Now, if that sounds familiar, it should, because back in section 4.1, exercise 19, you showed that the mapping that takes a polynomial f to its modulo p polynomial f bar is actually a ring homomorphism. So you might go back and take a look at that exercise because it will be used in the proof of this theorem. So again, the result is that if this f bar of x is irreducible over zp, then the original polynomial must be irreducible over q. Okay, this proof is best proved, or is best accomplished by contrapositive. So what we're going to do is we're going to suppose that we have the original polynomial that's reducible over the rationals, and then our goal will be to show that this f bar polynomial is reducible over zp. So anyway, we have this f of x which is reducible over q, and by the theorem that we just talked about before Eisenstein's criterion, that it tells us that we can take that polynomial because it has integer coefficients and write it as a product g times h, where both g and h have integer coefficients and both of them have positive degree, meaning that both the degree of g and the degree of h are strictly less than the degree of f. Now, by exercise 19 of section 4.1, which I've alluded to a little bit earlier, if we take the bar of all of this stuff, well, f bar would be g times h bar, but because this process of taking a polynomial and reducing it modulo p is a ring homomorphism, it respects multiplication. And so taking the bar of f is the same as taking the bar of g times the bar of h in zp. And then importantly, we haven't reduced the degree of f at all, because when we pass from f to f bar, because p does not divide an, it means that this leading coefficient here, when we pass to zp, is still non-zero. Okay, so that means that the degree of f is still equal to n here. Now, because f bar is g bar times h bar, that again is going to force the degree of g to be the degree of g bar, and the degree of h to be the degree of h bar. And so that means that g bar and h bar both have positive degree. So we have expressed f bar as a product of two polynomials G bar and H bar that both have positive degree, and that's tantamount to saying that the F bar is reducible over ZP. And that's what we wanted to prove. As a final example, we're going to show that this polynomial 9x to the fourth plus 4x cubed minus 3x plus 7 is irreducible over the rational numbers. So you can think about this maybe as being our f of x. And then if our prime p is equal to, say, to 2, then f bar x would just be x to the fourth plus x plus 1. Okay, now why is that? Well, when you look at the remainder that you get upon dividing 9 by 2, you get 1. The remainder of dividing 4 by 2 is 0, so you get 0 as a coefficient for x cubed. You get 0 as a coefficient for x squared. 1 as a coefficient for x, and 1 as a constant term. So now what we want to do is look to see whether this is irreducible over Z2. So the first thing that you would check, since it's a quartic, well, any polynomial, I guess, the first thing you check is to see if there are any roots in Z2, because roots, according to the factor theorem, give rise to linear factors. So you check and you see that there are no roots, right? You try x equals 0. And you try x equals 1, you plug both of those in to f bar, and you don't get any roots. So there are no linear factors. So then, just like in an example we did a little bit earlier in these slides, we now have to consider the possibility that there are two quadratic factors. So we write x to the fourth plus x plus 1 equal to a product of two linear factors, x squared plus ax plus b, and x squared plus cx plus d, where all of the coefficients here are in Z2. Now you might be wondering, why didn't I have to put some variables in front of the x squared? Well, remember that the only numbers in Z2 are 0 and 1. And because our original polynomial is quartic, the only possibility for coefficients of x squared in each case is to have a 1 there as a coefficient. And so then the question is, well, can we choose A, B, C, and D in the set 0, 1 so that this product of quadratics works out to be the thing on the left? And it turns out that it is impossible because, for instance, let's keep track of, let's just see what we get for cubing term, right? We have an ax cubed, and we also have a cx cubed, so that means that there are a plus cx cubed, but on the left we don't see any x cubed. Now meanwhile, if we count the x's, we have that there's an a dx and a bcx. So there's that many x's on the right. On the left there's one of them. And then for constant term we have b times d equaling 1. So we see from these three equations that b has to equal d has to equal 1. And if that's true, then what you get from the top two equations is that 0 equals a plus c. But if b and d are equal to 1, then this second equation gives you a plus c equals 1. And so then you get this nonsensical equation. right? So that means that there's no quadratic factors either, and we conclude that this polynomial f bar is irreducible. And that tells us from our theorem that we just had a moment ago that the original polynomial f is irreducible over Q. And that's the end.